Let me show you how to solve heat flow problems with a heat engine, okay? You always have a high temperature, and I'm going to call that TH, right? Then you always have a cool temperature, which sometimes, here they show a condenser, right? But you could just use the air, right? The atmosphere would be a cooler temperature than the boiler, right? Heat always flows from this, we call that QH, and then these engines always waste some heat, right? And then they do work like that, right? So we've got work that's going on, and there's a relationship here, okay? And that is that if we conserve energy, right, QH is the heat that flows from the boiler, TH is the temperature in kelvins of the boiler, right? W is the work done by the engine. QC is this is sometimes called the waste heat, and then that is TC is the temperature of the condenser, right, or the atmosphere. So this is our cool temperature here. These temperatures are going to be important when we get to the Carnot cycle, but so far they're not important. These guys are the things that are important. So we've got some amount of heat that flows from the high temperature reservoir, right? And then we've got a certain amount of heat that is wasted, right? So when you looked at that steam engine that I had in class, right, the wasted heat was all that nice steam that was going off into the air. Sometimes in cities, when they generate electricity, like in New York, they use that waste steam to heat buildings, right? So it's only wasted in the sense of it's not used to generate electricity, but it's, we can use it for something else, right? And then let me draw a little line here, right? We've got a branch that is work, we've got a branch that is QC, and then we've got a branch that is QH, okay? This is, by the way, called a Sankey diagram. And they're very helpful for solving these kinds of problems, okay? If you look at this diagram, you can see that if you do apply conservation of energy, or if you just look at the diagram, right, the QH, this branch here, that is QH, okay? Okay, QH is just QC, the width of this branch, right, plus the width of this branch here, work. Okay, so this branch represents the amount of work you get. This is like an energy flow diagram. That's how much work you get. This is how much is wasted, right? And this engine, by the way, looks like it wastes a little less than the work, right? This is probably 55% efficient or something like that, right? And that's just because this work branch looks a little bit wider than the waste branch, okay? So this is work. This is our waste heat, right? Sometimes we call that waste, right? This is from the boiler. Right, and then this is work. This is like electricity or whatever it is that we're doing with our heat engine, propelling our car. Okay. Now, our formula for the efficiency is, and they use like a little, what is that? I can't remember. I can't remember what letter that is, right? But that's our efficiency there. Is that I don't even know, epsilon? I don't even know. Okay, I should know. I should have known that before I made the video, right? It's just work done divided by energy input, right? So literally it's work divided by QH. The energy input is our QH. The work done is this, right? Useful work done. So that's what this guy is, right? Okay. Now, I'm going to show you a trick here because we can use these branch ratios to solve things. So let's do an example, okay? Actually, this isn't an example. I'm just going to show you the branch ratio. Okay, so let's imagine that we draw the Sankey diagram in a more helpful way, right? We've got the QC branch here, right? This is wasted. We've got the work branch. Then, of course, we've got the total thing here, right? Now, let's imagine that this thing is 20% efficient. That's not very efficient, but let's just imagine it's 20% efficient, right? If QH was 100 joules, right, the work done would be 20 joules. Therefore, the amount wasted would be 80 joules. Yeah? Or another way to put it is if the efficiency is 0.2, as we would do in more scientific circles, right? This work branch here doesn't look like it, but this would be 0.2, this would be 0.8, and this branch here would be, of course, 1. Right? The whole thing would be 1. Keeping in mind that the QH equals this plus this, right? So these branch ratios add up. Okay? let's do another example. Let's imagine that the efficiency is 40%, right? So 0.40, okay, that's my efficiency, okay? Well, this would be 0.4. This side would be 0.6 because 0.4 plus 0.6 would add up to 1. And then, of course, this branch ratio here would be 1.0, okay? Let's do another example. Let's imagine that this is 80% efficient, right? So this is actually 0.80, right? Okay, so now if we look at this, this would be 0.8. We'd only waste 0.2 of it, right? And there'd be 1.0 would be this stuff here, right? So you can set up a proportion. We can just use proportions, right? The heat input is to 1 as the work is to the efficiency, right? Because this is our efficiency, right? Our efficiency was 0.8, so here's our efficiency, right? And then this is 1 minus the efficiency, right? This thing here is always 1. This is the work branch is always proportional to the efficiency. The bigger the efficiency, the more work you get, right? And then this side is always what's left over, 1 minus E. Okay, now you have to use decimal efficiencies. Oh, I used E instead of the little symbol there. This is the same as this, right? IB uses this, so we should use that, but I didn't use that. Okay, there we go. So let me do an example. We'll do a couple quick examples here. Okay, a heat engine consumes 145 joules of heat and wastes 97, right? So if we look at this branch here, this is 97 joules. This is 145. Oh wait, consumes the heat. So that's our total one, right? Okay, consumes 145 is this guy. So then the question is, what is the work? Well, I'm going to use QH is QC plus work, right? And QH is 145. QC is 97, right? And then the work is like a great mystery. We have to add or subtract, right? So 145 minus 97 is 48. So the work is 48 joules, right? So this plus this adds up to the whole input, which is 145, okay? Then it says, what work does it do? Okay, we did that. We got that, 48 joules, right? Then it says, what's its efficiency? Well, efficiency is going to be work divided by QH, right? So that's going to be 48 divided by 145. And that's 0.331. That's my efficiency, right? Okay. And you could write that as 33.1%, right? And we didn't really use our ratio of our branch ratios for this. We just used this. And then we used this. So this was a pretty straightforward one, okay? Let's do one that's a little harder. All right. A heat engine is 22% efficient, right? So the efficiency is 0.22. If it wastes heat at a rate of 615 watts, now don't worry if it's watts. Remember, that's just joules per second, right? So what we're going to do is we're just going to go with watts instead of joules, right? So let's draw a picture of our little thing here. This is going to be 0.22. Do you see that this side's going to be 0.78, right? It's going to be 1 minus the efficiency. Is this branch, right? The QC. That should be a C there. There we go. Okay, so QC, the branch ratio is going to be 1 minus 20.22, which is 0.78. And then, of course, this branch ratio here is 1.0. Or I'm sorry, this branch width is 1.0. Right? So what I'm saying ultimately is that 1.0 is equal to, or 0.0 is equal to 0.78 plus 0.22. This is the ratio of these, right? If we put in 1 joule, we would get 0.22 joules of work. We get 0.78 joules of wasted heat, right? It's only 22% efficient. If I put in 100 joules, I get 22 joules of work, 78 joules of waste, right? So at what rate does it do useful work? And it's wasting the heat. Okay, so what I'm going to do is I'm just going to set up my ratios, right? Okay, QH is to 1. That's its branch is 1, right? As equals QC over 1 minus 0.22, right? Equals work divided by 0.22. And notice that I told you the waste. This is our waste. This is 615. So now we got to figure out what these guys are in proportion to that, right? So I go QC, so 615 watts, divided by, and 1 minus 0.22 is 0.78, right? That equals work divided by 0.22. So I can just set up this ratio here, and this should work, right? So I'm going to go 615 divided by 0.78, and the 0.78 again is 1 minus 0.22, right? It's the width of this branch. Okay. And then I'm going to multiply by 0.22. And I get 173.46. Watt is the unit. Work is that many watts, right? That's the rate at which it does work, right? Okay. The work divided by time really is what I need to write. Wow, it's really lagging. Okay, there we go. So now let's solve for what rate does it consume heat from the boiler. That's a QH question, right? Okay, so I'm going to use the same ratio. I'm just going to go 615 watts over 0.78 is equal to QH over 1. Ooh, I don't have to do anything. Okay, so 615 over 0.78 is 788.46. Over time really is 788.46 watts. Okay, so again, this thing is going to save you, right? This is your branch ratios, right? We go, high temperature is like all of it, the heat that flows from the high temperature. It splits into two branches. The work branch is the efficiency wide, and the waste heat is what's left wide, okay? That's what this is, okay? There are some more examples. I definitely would work through these examples. This is something that's going to take you a little while, and you should be really good at these. Because what we're going to do eventually is we're going to be able to derive the efficiency from the temperatures that these operate at, okay? And you need to be able to do that and do all these branch ratios with a Sankey diagram, okay?